Photoelectric emission. So we learned about the three other types of emissions in the last class, and now this is a fourth type, photoelectric emission, which is the main topic of this class. So what is photoelectric emission? Suppose we have a metal surface. Okay, on this metal surface we incident a light. Okay, we incident a light or radiation. You can call it radiation or a light. A light will come. Light contains energy in the form of photons, right? So they come, hit the surface, and electrons will get this energy and bounce out of the surface as photoelectrons. Okay, so the terms are really important. When a radiation comes and falls on the metal surface, electrons are excited and jumps out of the metal surface in the form of photoelectrons. So I'll read the definition. Photoelectric emission is when a light of suitable frequency illuminates a metal surface and electrons are emitted from the metal surface. These photo-generated electrons are called photoelectrons. So we read in the definition that this light should have a particular frequency, right? So I'll tell you why frequency matters in the case of particles, right? We have learned by the Max Planck's law that energy can be represented as E is equal to h nu. By the quantization of energy, Max Planck derived this formula, E is equal to h nu. What does this mean? Nu is frequency, E is energy, h is Planck's constant. So that's a constant. So if we were removing the equal to sign, we have something like this. Energy is proportional to the frequency. Okay, so energy of a particle is directly proportional to the frequency of that particle. So what does it mean by frequency of a particle? Max Planck concluded that radiation has two properties. It has particle-like properties and it has wave-like properties. So the particle you're seeing, like an electron, for example, electron has both particle and wave-like properties. So we can consider this also as an electron or this as an electron. When we are discussing phenomena like reflection, refraction, and such other phenomena, you can use particle-like explanation of matter, right? But when we are explaining things like diffraction, interference, we have to use the wave-like property of radiation. So Max Planck concluded that radiation has two properties. It can either be particle and wave-like at the same time. Okay, so electrons do have a frequency. They vibrate at a frequency, and that gives out their wave character. So the energy of a particle is directly proportional to the frequency of it. Even we have frequencies. We are matter, right? So we do have wave-like properties, but our mass is too big for us to show any such types of wave-like properties. Since our mass is too big, we don't show such properties. That's given by the de Broglie equation, but I'm not diving into it. For now, we understood E is equal to h nu. So that means E is directly proportional to frequency. Energy is directly proportional to frequency. So what is the energy here? Energy here is the work function of this metal to eject the electron out. What is work function? Work function is the minimum amount of energy required to eject this electron, right? So to eject the electron, we needed some amount of energy. The fixed amount of energy is called work function. So to get that energy, this light should have that particular frequency to get that energy, right? Since frequency and energy are directly proportional, more the frequency, more the energy. So I can write. So if this surface has a work function, we denote it by phi naught as 2 eV. Okay, the work function of this surface is 2 eV. That means that 2 eV is required for an electron to escape the surface of this metal, right? And suppose we give an energy of 1 eV. This electron will not jump from this surface because this energy is less than the work function of this energy, right? What if we give E is equal to 3 eV? Then definitely the electron will jump out and will possess a kinetic energy. We gave 2 eV for the surface, right? Then there is a rest 1 eV. The 1 eV will go as kinetic energy of this electron. Kinetic energy means energy when a particle is in motion, right? So this will launch the electron into motion, giving its kinetic energy as 1 eV. 2 eV was lost to the work function, 1 eV to the kinetic energy. So such a situation is called photoelectric effect, and frequency comes in the case if this energy, suppose this frequency was 5 Hertz, right? Suppose the frequency of this radiation was 5 Hertz. So what will be the energy? Energy would be equal to, we know the equation h nu, right? So h is Planck's constant. Planck's constant value is h is equal to 6.6 into 10 raised to minus 34 joule second. 6.6 into 10 raised to minus 34 joule second times 5, right? 5 times 6.6 is 33. 33 times 10 raised to minus 34 joule second, right? And if we were to convert joule second into EV, it would be, to make it into EV, you just multiply into 1 EV. 1 EV is 1.6 into 10 raised to minus 34 minus 19 joule, right? So divided by this and you'll get the answer approximately as 2.06 times 10 raised to minus 15 EV. You know, minus 15 EV means 0.000 followed by 13 zeros before 206 comes, right? So it's such a small number. That energy is really small compared to 2 eV, right? This is 0.00 something eV and our threshold energy is 2 eV. So we didn't even reach that threshold energy. So that energy would not be sufficient to eject this electron. So no photoelectric emission will take place. So we need a stronger frequency than this. Suppose we take a frequency of, suppose we take a really big value. Suppose we cut the 5 Hertz and we give a really big value like 10 raised to 15 Hertz. So that's a really big value. We just gave frequency as 10 raised to 15 Hertz, okay? So that would mean E would be equal to h nu, right? So 6.6 into 10 raised to minus 34 into nu, which is 10 raised to 15, right? If we do the math, we can get 6.6 into 10 raised to minus 19, right? And if this is in joule second, and if we make that into EV, it will be around 4.11 EV, right? 4.11 EV, and we only need 2 EV for the work function. So this can definitely excite an electron, right? If this is 4.1 EV, it will take 2 EV for work function. The rest 2.11 EV will go to this electron as kinetic energy. So this situation is called photoelectric emission. There's a lot to learn about it, such as threshold energy. We know what threshold energy is. The work function of when we are discussing work function in terms of photoelectric effect, we term it as threshold energy. There's no much difference between work function and threshold energy. Work function and threshold energy literally mean the same thing, but work function in the case of photoelectric emission is threshold energy. So in the case of photoelectric emission, we never say work function, we say threshold energy. And that to achieve that energy, the corresponding frequency for that energy is called threshold frequency, denoted by nu naught, right? Threshold frequency nu naught, and threshold energy is phi naught, okay?